Hello. Okay, I'm still getting stuff set up. Alright. So, if you want to, review the GitHub or anything, it's right here. It's also in the description. Blah blah blah. So, we're gonna be going over an update that I'm gonna push. I'm gonna do this, but it's for SuPosXt, which a lot of this is about to get changed. It's actually changed part of how it works, so a lot of this has to get updated. So I'm going to review, we're going to do a full review, so that way I can always come back to this later and just, remember it, blah 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 blah. So that's very ideal. There we go. So let's do this. Well, I guess what we ought to do, see if I can just pop up. I guess we need to show you what's kind of going on. So you can see it's stored locally. Let me, okay. We'll just do that, that's better. So, we can click, I'm going to type hello world. Actually, I'm going to type orange is a color, that's what I'm going to actually type. I'm putting a space in the wrong spot, so there's two spaces between is, so it says orange is space a color, all one word. Oopsies, whatever, doesn't really matter. It's gonna, actually kind of does matter, let me just redo it. Let's do it right, orange space is space a space color. See, and then we can finalize. So here we can actually see that we have something. We can actually see this has been grayed out. I can click there. It does see that there's something there, which is a blank space that we can finalize. So we could push in a blank graph immediately after, like so. It's supposed to say reset, I think, maybe. Orange is a color. Yeah, I just completely messed that up. Never mind. Orange. I gotta fix that. It's supposed to allow you to push in a blank immediately after. Now if I keep typing, it'll fix that. I'll go back to what it was supposed to be doing. Oh yeah, it's not changing back. It is not gonna. Okay. Anyways, we get this little bit right here. This is the graph. Oh, the hash. It's not that far yet. We're not even. We don't even have it hashing yet. So now we're gonna paste that graph. So this is where we're having problems. So, the actual graph, this thing right here. Well, we know what it should look like. I've done that by hand for the specific phrase, orange is the color. So right here, is that right here? Yeah, so what we should be seeing right here, and we can break it down that we know it should have this phrase, this embedded in the graph, which should look like this, 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 and this. And I think this is the graph right there. So I'm going to paste the one we got right below it and see if anything is different. We do see there is some differences between the two. But I don't know if this is what we should be seeing or not. So what we can do though is we can look for this. And we can do it where we only search within inside this phrase. So in the selection, it did not do it within the selection. Oh no, it'll only change within the selection. That's right. So no, it's not finding that anywhere in there. And then we can say, okay, what about this one though? Nope. Also not finding it in there. We're going right back up to the top. So we're getting is 11101. So 11101 0011 0011. And then I got the 001 01 01, and this is where it's different. So we are getting some kind of encoding difference somewhere. There's some kind of error potentially happening. And we can see that when we originally did this, we did get an actual error. This is what we saw then. So if we was to break this down, this is 1, 2, 3, and 4, or null. So null, 3, 2, 1. And then we have our identifiers, so we can say these two are indicators, indicator, and then indicator. And then from here, no, nothing there, from here, right there, we can say that spot, we know for sure, is the, that's the Stephanie. That's the Stephanie phrase. So that's basically like an index, is what that is. And now I have an idea of what to do once we get this working. Once I get this graph to work, we're gonna get it set where we're gonna entangle that graph with series of randomized information. And I want it set up that if someone was to run a graph or one of these specific type of hashes that we're going to build with it back into one of these, that it would polymorph that graph and just basically encode it into layer, um, with the difference between the previous to now. So we won't actually know what's in between. We won't know if there was anything in between. We won't ever be able to tell that until after we unwrap it. And when we go to unwrap it, the index would be unusual. Wouldn't it be an index like this? It would be an index that's very unusual, which would be an indicator to let you know, hey, this has been wrapped. And with it being polymorphic, meaning like we could run it through various different types of wrapping layers all at the same time. So say for example, you want one that is the standard, but you also want it to be like base 58. So you would have a base 58 multiplier at the end. So at the end, it ends out being a base 58. Well, we could take that and we could apply that as an input and then have it output as something else, and it would just basically wrap what we got, right? But what I'm really saying here is that we can just wrap this little bit in a way that is in its own compounding code. So we'll basically just run this one little bit. So when we'll run it through and it says, hey, this is already blah blah blah, it'll be able to take this bit and do a sequence of encoding just for it to give it its own table, its own index, and then put that back. Right? So when we're decoding these things, it would look natural. It would just look like a standard one. You couldn't tell there's multiple wrappings until you start unwrapping it, and then you get to this point. And then it would see this, and it would go, oh, and it would hit a different whatever, and then it would process that, and then it end up with a different output until it gets the output that's a standard output like this, something it's expecting. And if it ends up with nothing, and it can, then what it can do is you could reverse bifect and just go to the last previous step and just assume that was the last step because now we know it is, and try to end it out there. And you can keep doing that until you end up back at the beginning and with no output. And if that happens, then you can go incompatible. So there are ways to proof check these ideals concepts, but now I just got to get the dang thing to work right. So that's what we're doing now. Okay. Now we're at the point, about 15 minutes in, we're actually going to go over some of the code. Because we kind of showed you what's going on. So if we're looking at this, we can see there is some kind of error during the encoding where something's not quite right. Maybe it might be during the phasing when we're changing the phase. And that's my biggest thing, is I think it's going to be when it's being phased over. So that's a whole process we'll get into. And the output. As we can see, it's not mining out the rows. It's like it's getting lost or something. One of these, I think the top one is supposed to be like what we're wanting to see, like decoded. And the bottom one, it's just supposed to be this decoded. No, this. It's just supposed to be... No. The bottom... Well, actually, I don't know. Yeah, the top one is the one that is being imprinted. It were being built based on the detangling structure. The bottom one should just be these phased into correct phase. So this should be over here, just phased correctly. And then for all of those, and then this up here should be the actual steps. So like we can actually see that it noticed one thing. It's at 17, which 17 loops to decode. It noticed one thing, 11, which is not correct. There's no single 11 in here. There's triples, no double. But if we look up here 1100, and if you was to look up 550.01, which we will later, it should be that. But if I look down here, it says that it actually graphed 770. Remember, it's 1100 is what we have. So 1 1 0 0. So we're looking here for 1 1 0 0 at 770. So let's go. Let's find those first. I didn't see a 1170, did you? I see, okay, 0, 1, 1, 1. So 1 0 1 0, 0 1 0 1, 1 1 1 1, 1 1 1 0, all 0, 1 1 1 0 1, 1 0 0 1. Wait, 0 1 1 0. Yeah. So none of them are 1 1 0 0. So now let's go look up. And we'll see it's a 5 set. 1 2 3 4 5. So there should be 5 numbers if it was that. Which we don't see. But we did see 11, didn't we? Doesn't exist. And if we go 1 1 1, we'll see those are all 3. So output really doesn't make sense. So it did not actually graph that. It was graphing this one, but it's still not. It's just not making any sense. But if we look down here, it's able to see all of Stephanie. So Stephanie, right there, it sees Stephanie perfectly. Okay, that's my index. That tells me in what order everything's in. Okay, and then you go, is this and this the same? They are. So there's no errors. I think should be correct. 17 loops to decode. And when you see it's a 4-step multiplier. So I mean, and if we look 0 1 0 1 and 0 1 0 1. Okay, yeah. See error possibilities, 0 error possibilities. Now it says it went through 53 loops. And this is all we got. So there is a setup in here to where if it tries to over loop or just it can't figure out, it's like it got nothing left to do. It will try to do the minimum number of loops. Then it will basically go give benefit of a doubt, and based on the amount of output, it will either try to loop harder or loop less, and eventually it will kill itself. So thankfully, for a 17 set loop, 53 seems more than reasonable. It's over double. It's about 2.5, right? 1.5 extra times. So it probably went through the whole thing more than one time. Went through, as it goes through, it removes as it does. So whatever it picked up, which we got to figure out what it is as a 1100. I'm wondering if it's 110000 because I don't have any 6 sets. But I'm afraid it might be what it's saying. But so it's saying that it picked up one thing, which probably gonna be whatever this was. Which we know it's only a 3-step. But because 5501, we didn't check to see the heat map. Right, we didn't check the heat map. A, B, A, B. No, it's gotta be all of them. One of each. A, B, D, A, B. Okay, so this is close. okay, I could see here it went A, B, D, then it went C, and then errored out and canceled. I could see that happening. So is there in here a 1101 and then something else for these numbers? Okay, so nope. 11011. Oh, good point. There's also this one, P. So O and P. Yep, O and P. Gosh, more of these, holy crap. Yep, O and P. Now, let's see, can we find... What was the very first thing it should have done? Match case. Work backwards. All ones. A, B, A, B. This makes more sense here. It just did A, B, C, D instead of A, B, A, B. But why did we get 0, 0? So, let's go look at our output. So, let's see. 1, 1, 0, 0. So, when it pulled the very first one of each, we had 1, 1, 0, 0. So, it really did try to do, was it 7700, 777, 770? Yeah, I think it really was trying to do O, but it just went A, B, C, D instead of what we're seeing here, A, B, A, B, the actual heat map. It's not doing the actual heat map. Oh. Coding isn't using the heat map at all, actually. So... yeah, O would be looking for all ones as instructed. Is that 5 ones or 4? That's 4, okay. Alright. Okay. Anyways, going back into the actual describing the code, now we know for sure input's a little off. Output isn't mining. Let's see what we got. So we start off naming off a ton of variables. I don't even know if all these variables are even being called anymore. Yep. Well, I mean, not all of them. That one gets called, right? Although it gets called quite a bit later on. Ones that I don't know that get used are like bearer, goober. This one I know doesn't get used yet, but it's going to be used later. This is going to be used to make for the polymorphism. This one, n-type. Am I even using n-type? Oh, I am. Cool. API. Yep. Definitely using the API. .5 C box, A box, B box, D box. Wait, box. Am I still using the individual boxes? Yeah, I don't seem to be using the boxes anymore. using past fog. Nope. Heat map, I'm using row map. I might not be using row map. Not. Centers. Nope. Leg. I'm not using leg at the moment. Gym. Oh yeah, gym gets used. Okay. So boxes. Not being used. So basically we just go in and we start saying, hey look, at the very beginning, if the main input, the one we first come on, got nothing there, or if, no, if it's set, the style is set to carrier news, so if it's basically set to its standard output, its standard text font, whatever, which is like, there is a way to actually get to process to go back to that. So whenever it is in that, we want it to have nothing. We want it to just blank. We want to basically reset everything. So it resets quite a bit of stuff. So is this resetting everything that it needs? So queue up lets me, I can search it up later when, like, I got a large portion of stuff done. It's something that we can come back to question, like, there are questions throughout the thing, like, am I doing this right, am I doing that wrong? And we'll post a bunch of those today to use for references later. So then here we can see we start filling in the dots. We want to clear out the dots in this case as well. Dots is actually around the thing, so like the input. So then we say now if the alt input is the same thing, like the basic output, same thing. Just clear everything out, bro. Also clear the dots, reset the dots. So now we're going to the actual Fullhouse function. This is going to do a handful of things. So the very first thing it tries to do is it checks tracker. It says, hey bro, is tracker 45 or more? 45 is like this base number that if we encode 45 characters in this manner, we should be able to output a block that is less than 255 bytes. Or, yeah, it should be like 254 bytes. So just somewhere under 255 bytes. And that's a very important thing to do. Like, it's something I always do with encoding block. When I get a type of block, I want that block to be within 255 bytes. It's like, it's my thing. And if I can get it smaller and smaller, it's the ideal. So 45 is the magic number that we are looking for under tracker. Tracker is literally just looking how many times the buttons have been pressed. So we're allowing 45 characters to be put in, knowing that most characters, and that's based off the math that most characters are going to be a certain type of, or a certain amount of bytes on average. So it is a chance that we can get a bit over, chance we can get it under. And we can see we induce gem, and we take gem back to a state of 1, which we're using gem as a really weird indicator, because as you can see, these are two separate things. Like, we could just say, hey, if this happens, do this. But there are other things that can happen to make gem a completely different number. And so that is the point in reasoning where we have to reset gem to 1. And then we have a thing in here for gem to be 1, because there's other times that gem can equal 1, and then when it goes through its loop on those times, it needs to activate this, even if tracker is not 45. Because I've gotten questions on this one already. They're like, well, why are you going to do that right there, and then immediately do that here? It's like, because we can change gem later without having a tracker at all. Like, we can have tracker be 1 and invoke gem to 1 and finalize a graph is the ideal there. So it's an additional set of ways. So you can always, we have 2 ways we can end a graph. We can set the tracker to 45 or more, or we can set gem to 1. Cool. And we can see when we set gem to 1, gem sets himself back to 0. Also sets a couple of major protocols back to 0. So it sets the length of STE to 0, and then it defines that length, and it sets this one to 0 and defines that, sets this one, defines it, sets this one, defines it. When we were setting and defining at the same time, only part of them, like every other one was being defined. Setting them at 0 and then defining them does 2 things. It tells the system right off the bat, I want this to be a number. Okay? And then the next time we give it should be a number. And from this process, it has allowed me to end up with a number. It also ensures, separating it like this, it kind of forces the computer to do one extra step, and that ensures that we don't miss every other one like we were doing. And I know that we could be calling them sooner, like out here, but we don't want them to exit Fullhouse. So everything that we call, actually these we don't even want to exit gem, this gem structure. So we only call them within this structure. Actually, everything you're seeing that's being called right now, of all these vars, they do leak outside of function, but only down. So I can't leak up. So tracker right here can't leak this. Anything before this can't be leaked. And that's great, which means, A, I can't just do stuff without running the program. I have to at least run it. I have to put something in there, let it do its thing, if I want to try to manipulate it later. So it's like a security check thing. I could go with a more stricter one, like Lin or something like that, and ensure it never leaves this gem protocol function at all. But I do want it to leak a little bit, and not all of them, just some of them. So maybe later we'll go in, we'll change some of these to Lin, or something else. There's another one we can do too. But anyways, so we have a target 2 and an SMSM. As you can see, that's called see me, set me. It is an in-step programming key that we are not using yet. We should be using this. This is definitely something that I'm not taking advantage of. It's just like how I know I'm not taking advantage of heat maps later, but I don't know how. Same problem here. I'm not entirely too sure what all more I can be doing here, but I do know the way we got it set up is that we could allow this to modify anything, any variable, any value, anything at any point in time, which is kind of cool, because I'm actually been considering like all these down here later on being like plus SMSM, plus SMSM, plus SMSM. And when I first did that, I was getting stuff where if it was a 1, it would then add it and just be like 10 instead of 1. You know, it's 1 plus 0 is 1. It was just adding it to the end of it. Just it wasn't adding it as math. So at the moment we're just not using it, but that is the point, is that eventually we'll have to do a higher math function to ensure that that's a math product and ensure the output's actually a number and other bull crap. But it's there. It is usable in the future. So ST1, ST2, ST3, ST0. So EDC3, for some reason, don't know why it happened that way. It happened that way. We see E is R1, D is R2, C is R3, and 3 is 0. Now, if you look on most American key sets, it will be 3 and down to the right E, down to the right D, down to the right F. So they're all like in the same row at a diagonal to the right down. And I think that's where it came from. And what we've been doing is been putting a null to the bottom. And that's a process that is done very commonly in very many things, but we're not heavily used to it. What we see here, there's ST5. I have no clue. Do we even use ST5? The only time it's used. Get rid of it. Oh. Wait. I just realized ST5 and there should be an ST4. Okay, so we need to make a note. It just hit me. So I need to keep that in mind. When we were manipulating later with SMSM, we can use these as bucket holders, so we can dump like an entire bucket in there to then manipulate as we put the manipulation output into the bucket we just cleared out. Or we can do a bucket manipulation the other way, drop it into a 4 or 5, and then like we can drop it. We can do bucket manipulation with 1, drop the answer output into 4, and when we're done, we can take 1, drop it into 5, and take 4, drop it into 1. We have a fresh new 1. We have a copy of 1 and 5. So if something goes wrong, we can recall it. And we can do that at least 2 times. I mean, the next time we'd have to be a little bit more strategic on how you do things, because you gotta dual manipulate to swap them inside and out, but it is possible. From within inside of each other, the same container. So 2 of these buckets could be swapped in the same semi-semi protocol. Or like in the same loop. Alright, so we are setting target to 0, guide to 0, and current length to 0. Now, here it says current length current was originally set to 2. So keep that in mind, this has been changed. So we also have oof. Am I even using oof? I am. Note 1. Okay, I don't know what notes are. Notes. Temporary variable for swaps and changes. Ref reg y or ray. As you look on your keys, FTGY, FTGY, are all right next to each other. They're all in like little spots, weird, you know, rubicoid, or I don't know. Rhombus. Yeah, we got rhombus. They're in a weird like angled rhombus. So, but they're basically cuboid. So 1, 2, 3, 4, 5. Oh, because E, yeah. Yeah, the E is the odd one out. My bad. Usually cuboid. And those are, as you see down below, right below it, we see re equals gwem, ref equals gwe, ret equals gwex, reg equals gez, ray equals gwet. And if you look at those, if you look at these GE things, WM, WK, X, Z, ET, yeah, you'll notice that pattern a lot more. So we're using WIM. Yep, definitely using WIM to find out when. We're using PD1. I think PDs are product displacements. So that'd be row displacement 1, 2, 3, 4. So yeah, those should be getting used. Yeah. Guam. Yeah, I think all the guams are being used. Yep. Guegui. Okay, so all that should be getting used. Let me double check this last one. Yep. Okay, so these are all being, so these ones back here with all these numbers, they're being used to basically talk about how far away from the read head we need to go to do things. So a lot of what we're going to be doing is done in a process of two major systems. We're going to have a general turning machine and a general counter machine. So one's on, imagine like you're sitting down and you have one on one side, one on the right. Counter on the left, turning on the right. And the way it works is we're checking buckets in the counter, and if the bucket is empty or full, right? And then we also check the turning machine, same thing. And then if there's something in the turning machine, we go to the next, we move both of them to the very next bucket. And that's kind of the thing is, one of these can be moved all the time. I can't remember which. As we go through, we'll figure it out. One of these can be moved all the time, and then once something's written down, once something's written down, that machine turns. I believe it's a turn machine that does that. And once that happens, they both have to go forward. And this forces us to always be moving towards the end. And this allows us to compact how we do our looping, so that way we can like loop through the exact same process over and over and over and over without messing up the original loop cycle, and without having to have any kind of breaks or anything like that. So this will actually allow us to perform faster micro loop processing inside the main loop. So now we're still within this statement if gem, so we're still inside the gem. We're now starting another if. We're now compounding our statements, and we're saying, hey, look, if you see after all this, and this, you know, have this situation if current length is actually less than what's inside the stem length, because current length is set to 0. If there's anything inside stem length, then that means that it's gonna be more than 0. So then it will activate. So if there's something left in that spot, meaning there's something left in this row 1, we will run through this process, and it will set the current length to that, so we can perform the microprocessing that's going on. So basically, all of these like little processes like within inside here can happen individually within the main loop processing. So there's a main loop process that it goes through over and over and over and over and over and over. Okay, and each time it has to loop through that, there is a major power cycle. So what we do is we try to perform as many little cycles within inside that does not affect that, to not cause a major power shift until that loop is over. Sure, this gives you how many loops it went through, but it's also designed to purposely go through extra loops. So even if it gets it right, it should at least check twice to make sure it got it right. So we're guaranteed for them to at least be of some confusion even in their correct output of like how many loop orders there is, how many loops it went through to get the whatever. What it can't do though is it should not be able to tell you how many microprocesses are happening in between there. Now they might be able to figure out if certain microprocesses are happening based on the length in between each major loop. So one of the things that we try to do is we try to set null probes, where we set an option where if any of this doesn't work, just do this last thing, and the last thing is do nothing. And then that is a point where we eventually want to put in a wait cycle, where we can guarantee, where we can actually do a volumetric wait cycle where it's like, last time we noticed it took 45 seconds, this time it's going to be like less than 13, let's make this wait like another 30 seconds. And just really ensure that whatever your last highest cycle rate was, everyone after that is similar. even if it's decreasing, doesn't matter. You can always make it look like it's increasing. I mean, all sorts of different things. So that's how these are being broken down. So now we're in the microprocessing of there's something in row 1. So what do? Is we go through this microprocess of a do action that it can take target 2, make it target 1, target plus 1, which targets 0, so it's going to make it 1. Right? Is target 0? Yep. So it's going to go to 1. So then it's going to say if target is equal to guide and guide equals 0, it is in a cleared state. Because I was about to say, wait, why are we not using zeros as the start? But yeah. So basically, if guide is at 0 and target is 0, there's nothing in there. So it will push a 0. And then it will move our guide to the next operation, which would be 1. So, Oh, sets key bit. So 0 is a key bit. We need that there. Okay. And it's not setting 0. It's actually setting the first spot in row 1. It's setting that as the key bit. But according to this, we would never get here because target and guide would have to equal 1. No, target 2 equals 1. Target equals 0. Yeah, so this would activate. Yeah. Okay, so that'd be the very first thing that activates. Yeah. And then if guide is less than stem length, we are going to then say R1 target is not equal to R1 in the second. Oh no, if these are the same. If the target we just looked at and the next target are the same, push this. If not, push this. If ST1 has nothing in it, send a 0. No, we shouldn't do that at all. We shouldn't be sending anything. No, we're setting. Oh, this resets. That will reset it because it's normally a array. Because there was originally a array. It moves target forward, moves guide forward. Oh, so even if this is 0, it will just keep moving forward since it was activated anyways. And while guide is less than or equal to actual current length. So once it goes over current length, we're done. Once that happens though, we'll reset all 3 of these, target, guide, and current length, back to 0. So then, the very next thing we ask is, well, for the next one, and we go through should be the exact same process, but on row 2 instead of row 1, down to a fault. Should be exactly just slight differences. yeah, it does that. It's all 4 rows. So what that does is it looks and it says, okay, because this is the finalizing into B process, and it says whatever the very first thing is, we want to push that there, and then after that, we only want to put a 1 if it's the same as before, and a 0 if it's different. We don't even care what it actually is. That's all we care about. Is it the same or different? That's it. And that's all the recording. So when you look at the graph and you see 1101, well, you know it started with a 1, so it starts with a 1. And it was 1101, right? So the very first 2 are 1s. So it's a 1, 1, because the second one is the same as the first one. The next one is a 0 because it's different. But then the next one we see is a 1, so that's also going to be 0, so it's 1100. 1100 transmutes to 1101, and 1101 transmutes to 1100. We set up a bunch of these 4-block boxes, and when we're hashing them out, we actually cut them in half, and we put the back end and the back end of the previous and the front end of the next one together, and this creates, and then that's basically entangled in a manner to where we were talking about earlier, we can go through the same process and we keep an index of that setup, and we can actually, because we can break that in half, we can break that in half, we can break that in half. We can get to a point where 1/5 of the first character is encoded to 1/5 of the last character in the loop, and we can even like encode previous encoding wrappers to current as a previous input, so it'd be like the entire previous and plus the very first character of the next one, or the front 2 characters of the next one. So we have these little boxes that we can subdivide multiple times, indefinitely almost, allowing us to do quite a bit of fun there. But that might also be where some of these errors are coming from. So if we look, Guam is the average loop cycle, Gwem is the start for D1 and D3. Gex is the start for D2. Gez is increase for next on D1 and 3. Gwe is increase on D1 for inside D2 position, or increase D1 for start of D4 position. Okay. Gwe is second position for D3 or 4. Zum is the base scale of Gwem and Gex and Gwe to the next level, following fine. So as you can see, some of these are used specific. So we need an average loop cycle. This is the average loop cycle. So number we need to know that we need to base our loops on, our macro loops. Gwem is where we start for D1 and D3. Gex is where we start for D2. I don't know how in the hell we started D4 ever. There's nothing in here to represent the start of D4. No, what? Increase D1 for start of D4 position. So, to find what D4 is, you take D1, you just increase D1 by Gwe to get D4, and you increase D1 by Gwe for the, I'm assuming, increase next position on D2. And okay, so we have specific ways we can add these things together to get different things. So finding D1 is just go Gwem, and then Gwem plus Gaz, and then Gum plus Gaz plus Gaz. To find Gaz, then we find Gaz. That's so side A. Oh, side A, and then Gaz plus Gaz plus Gaz plus Gaz is side B. and then start position, add 3, and then add 3, etc. So this is the breakdown. So it's start position, and then add 3, and then add 3. And you can keep going if you need to increase the size, but this was set to a specific size, so I only needed that many each time. 2, we go gex, gex plus gez, add gez again for the next one, set it gez for the second, and this continue on. Gwem, gwem plus gwa, blim plus gwa plus gwa, start at gwa, gwa plus gwa, plus gwa plus gwa, same thing, right? For 4, it's gwem plus gwes, blim plus gwes plus gwa, blim plus gwes plus blah plus gwa, and then gwet is the next set, 4, and then gwet plus gwa plus gwa plus gwa. So we can see here, we have it set up to where we just have to do these things. We can set all these numbers. We don't have to guess. We don't have to. It's set up in a way to where it is like this. And then if you need it, if it expands, you just follow this pattern, whatever this pattern is. You just follow this pattern. See, this one's like add 1, add 1, add 4, add 1, add 1, add 4, add 1, add 1, add 4, so on and so on and so on. This one would be like add 1, add 1, add 4, add 1, add 1, add 4. Yeah, see? While the other ones were add 3, add 3, add 3. So, it's really cool. It's just your starting position is a huge difference here. Gwam being start here, gex being start here, but then gwam being again start here. It makes me wonder if gwam ever changes over time. Because if so, then that means that gwam is being used as an index position. So then these are like 1, 3, like 1, 3, 3, 1, 3, 1, 3, 3. So then we can assume that this is 1 was position 1, 1, 1. So where's the 4? I don't actually get where the 4 is ever set in here. It makes no sense after that. And then see here, I got another reminder of what frit, regret, all these are. So, okay, we see gwem is 0, gwe is 1, gex is 2, gez is 3, gwe is 7. Okay, so we actually have them defined as actual numbers. 0, 1, 2, 3, 7. Okay, that makes more sense of how that's for. Okay. 2, 1. And then to get to the next start, it's 4. Okay. Oh, that one's 7. Okay. So node pound will be detector arrays for determining the detectors at the beginning of the graphing. Find the longest set in the inrun. Gwam is the average cut to find the longest array. The longest array sets loop max scale limit. Loop max scale limit. So here is where we do the trickery to figure out the longest possible loop needed to figure out whatever it is we're trying to figure out. And this is guessed each time we run through, or this is calculated. No, this is only calculated for enclosing it, but it's done each time this microprocessor is ran through. That's nice. That's nice. There probably is a way to manipulate this, but I'm not sure how that would be yet. It has to have something to do with the difference here, because we can build that difference in different ways. There's 5 right there, right, and 4, and then 2 gez to make a 6, but I mean, Alright, so we see here PD1 is going to be gwam plus x. So we are looking at specifically, what was gwam again? The average cut to find the longest array. And then we're starting a gwam 2 and a gex 2. These are different manipulators. And if we look at gwam plus x gwam, and when we see x gwam is a scale base, it actually is it scales bases. So these must be additional basings. Only pulled from this record state changes, not the actual row arrays. Prep, detector, check solutions, or sections. So the PDs. We got all the rows and stuff. Okay, so if rar equals or is less than 3. Wait, what? When did rar 1 get set? A long time ago. Okay, so it should activate, and it would do GUI equals these things. This gives us a number, so this will give us, let's, 3. And then it will say rar1 equals rar1 plus 3. It's going to be moving it that distance. So then next time it comes up, it should not activate, and it would say goo equals ges plus ges, and rar1 now equals 0 again, because next time we need it to go back to. Okay, that's pretty nice. So it self loops back to itself each time. It's performing a basic counter counter processing, and it's going to be doing that for each of these each time to ensure they get their first one, and then they get their second one, and they get their first one, then they get their second one. Alright, cool. So then we do the next step, and now we're looking at the length of Guam for that for each row, where we're basically now saying, okay, so Guam, if Guam is less than the length of the row, basically we're trying to find out if there's enough room to pick for Guam. Okay, there has to be at least Guam in there to pick it, which is re. So if there is at least that amount, from my look, it should be that amount plus 1. Else we want to just take, if rar is less than 3, we want to take Guam. Else we want to take ges, which is 1. So we can. So this does allow us to basically take the easy route first. We're basically able to say, hey, if this isn't enough room for this, don't fucking bother. Okay. But if there is enough room for it, we're going to take it. If there isn't enough room for it, the next step is, well, 3 is the next step lower, right? So if there's less than 3, just grab this 3 right here. Else, just take 1. Pretty simple. And this allows us to step it one at a time if need be in microprocessing. Now this is the point where I'm talking about this step in here can cause that additional, well, it took like 13 took 13th of a second longer to do the first loop than the second loop, or the third loop than the second loop. It took 14 microseconds longer, and so that's what can make your variables in that loop process, your total loop process, little things like this. And we have one for each of these scenarios. Right here. So this is technically one that it's a variable processee, and this is a variable processee. We have 2 variable processee per single one of these, and we have 4 per detector, so like 16 of these things. Now we can see we're done with those steps. Yep. So we've done all the detector checks. Now we are doing the next time. When we see when we were doing detector checks, we were pushing stuff to note. Okay, so only import from the recorded state changes, not the actual row arrays. So we're going to take goo is greater than this number. We need to do this. Otherwise, do this. Wow. What was rough? How much? 1. And this is the wanted action. Goo. It's the fly adjuster. Wow. I'm moving by 3 each time. That's a common number here. Same thing. Same thing. So all this is really doing is just I have a feeling we're pulling from the wrong spot. Because it said to not pull from the main, but this looks like we're pulling from the main. Okay. It's taking care of various different scenarios if we don't have enough room for pulling the number we're expecting to pull where it's located. Now here we are finding the total number of ones for comparison. And see, now I know, like, this is the detector stuff. This stuff is working. I'm just checking to see if stuff is divisible by 2. That's it, really. And then by the time we get there, it says finish graphing. So this is the next part, finishing the graphing. So we're using bear to determine first stop can't be done till end, so we need to add previous data here. Whoa. We're actually moving full stop around. So we're using bear as an indicator to prove some information, and then we're putting that back into full stop through a two-step process. So So if PD has nothing in it, do nothing. Let's see. We'll see what it means. It creates a standard power draw amount and timing and a couple other things. So otherwise, do this. So there's nothing there, do nothing, otherwise do something. Do specifically this. So we're defining graphing variables now. We're using let in some of these now to create a loop process. So we can, looks like we're turning arrays into strings. Yep. That's right, the compression had error, so I had to pause compression for right now. Compression gets used to create hashing later. When you start to see the starts of hashing happening. Goober is used as a type of check method to actually graph out. And two different considerations though. So, oh, that's right, because reborg. We're not using reborg yet. So Goober just is if it's this is a previous hash or not. They have a previous graph inside of it or not. Just outputting everything in order. Reset the tracker. Reset the workers. Is that all the workers? And the wrapper. So Gibbler. Okay. Now we are at the actual first process. Oh my gosh. If Gibbler equals Gibbler equals whatever's in the input. Add one to tracker. Set some new variables. Your C means set way down here, so this has to go through to be able to even use it, or else you will come out as a non blah 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 blah. Oh, this is actually supposed to be set for error correcting. That's Bruce, I didn't need it then. And here is a point where we are changing to no, because now we got something in there. Oh, this is just information for me to remember what's going on. So when I say Kimmy is Gibbler, specifically at that letter counter spot. And Gibbler equals, if Gibbler equals nothing, we set that carrier new thing, which will automatically do a bunch of other stuff, as we saw before. If discretion equals 0, we make sure Kimmy equals nothing. But it doesn't change Gibbler. Okay, so this is how we're defining the HMAP as we go, so that defines how we set up this inside the HMAP. And this just basically tells us, this is the instruction set on how we want each letter to be broken down, how we want each letter to be defined, and all that. This is the base set. It needs to be modified and adjusted because some of these are, there's duplicates been found. Or I accidentally used the same, like, set here for these. Here's the different Machero values. Here's the different expected output types, what they mean, all that. How the grid thing that we can't see looks kind of like, how to envision it, row 1, row 2, 0, 3, 4. And this is where we're placing stuff inside And it's really works. We see this visual, and you see this here, but we don't. It's just weird. It's not used. It can be, but it's not. So like if reading left to right, it's like that. If you're reading top to bottom, it's adding. So we have a way to determine direction. We can get unique numbers in the same spots and things like that. So for example, we see a 6. We know, for example, that it's the top and the bottom added together. So here and here is the example. So I believe it's 1 and 2 is 6, and then 2 and 3 is 9. So we just have a way of like, okay, if it's this direction, if it's up and down, we have a set of number sets, and if it's left and right, we have number sets. And if you notice, this grid doesn't go past 4, so 5, 6, 7, 8, 9 can be used for up-down determinations. We can easily determine rows versus columns. I don't actually use it. I don't need to. I just use like some part of one of these, I think. We don't have any of the second or third or fourth sets in here yet for the detector setup, so that needs to be done still eventually, but we gotta get working first. Because basically, like, if the detector arrays are 1 through 0, it would do things a certain way. If it's a 2, it would do things a different way. If it's a hex or a hash, or basically it sees letters inside of it, it will do something different. And then, like you see here under P1, if there's specifically a hex-like value, it will perform, it'd be able to perform something very specific. So these are just like how we expect to be doing things. So here it's like the standard way is 0 through 1. If you see a 2, it just like says a blah 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 blah. And what it's doing is that we will, during decoding, that will be like, oh, if you see a 2, you need to do a different type of parity check. If you see a hex-like, you need to do a different type of parity check to ensure that we're checking the right things for what we have. I mean, you might have to do another step in the parity check is another thing too. So trying interaction to some ones are even and some of all ones in the subgraph are even. So you read that, right? So this trying action, what 2 actually means is that the sum of the ones are even and the sum of all ones in the subgraph is even. So say detector 3 has a 2 in it. That means all the ones in D3 are even, and in all, so we can have any detector spot be a 2 to find out one really special thing. All the ones in this subgraph totaled together are even. Even if our detector 1 slot does not say 1, which would be the other way to determine that. I mean, it'd be a 0, and that's the other way to determine that. Like, the detector 1 is set to make sure all of them equal 1. So that means that without detector 1 considered, without any of the detectors considered, it equals, all of them equal 1. So without the detectors considered, so no D1, D2, P1, D3, without those considered, all of the ones are equal. And then that could give us, we can put that in any one of these rows to tell us as like a key identifier row. This is the row that all of them are even in. So none of the other ones are even in this row, but altogether they end up being even without considering any of the detectors. So it gives us a lot more information. So we could have like a 1 here. Like we have 1 in the spot 1, or 0 in the spot 1, saying everything's even, bro. I didn't have to change this, didn't have to flip this, right? But then we can have a 2 in detector 3, and it would let us know that, well, D3 did have all even, that detector was all even, and we know that if we don't consider any of the detectors, everything is even. So it gives us more information to hunt and correct errors. Not just hunt, but correct errors. We can actually start forcefully correcting errors this way. So blank x number would be a hex-like value. That's just one example. I have to actually change the way that actually set up. Point of data times graph or extended key equals extra point of data. So I'm pointing out here that if we have enough of the data, we have a single point of the data, and we multiply that by the graph's atomic value or its extended key, it will actually give us an additional set of information that we might not be aware of. We can use this extra set of information basically to give us future tips in the future on how to correct things that we don't understand that was messed up. We don't know exactly where it's at. That's how it works. So we can take row 1, and we'd hear it later. Row 2, we'd hear it later. The only thing we're hearing right now is the programming key. That's it. So programming key is adhered. Cool. Nothing else is adhered at the time. So we're looking at the subgraph. We're actually going to build the subgraph. Cobalt is the reading head. And so we can see here, this is basically the same thing. We have a reading head, and we can extend past the reading head. And we can also go to what should be equal of the reading head, or down to what is now null. Because we're going to be doing the same thing. We're going to be cutting stuff as we go on one side. And so we either need to be able to reset that completely with like a yo, or we need to know whatever the considered null is, because rail could be changed. Debol, for example, does change stuff like that, and step length isn't always, well, cobalt is not always going to be 0. Cobalt is the base. So say cobalt's at like 55, yo will always be 0, and bro will always be whatever the base of that is. So brow can be changed, yo can't. Mufmumba. So we can see here, we are stripping everything down to just 0s and 1s at this point. So we want Steph, and we only want 0, 1 on Steph. Yeah. So we just want only the 0s and 1s. I had to make sure that was right. Okay. It still can't map a single character. So we're using yo to set oi. No, we're setting yo now. Oh, I guess rail's one that doesn't change. So yo's now changed the oi length. And what is oi? It's the heat map. So now we can see how. Oh, okay. This is encoding, right? So we can find out how long the heat map actually is, and so we can say, hey, there's nothing there. There's no heat map there. In that error catch, we do this, which doesn't change anything. It just processes information a little longer than it normally would. And then here we can see it does each one of these for basically everything that can be pressed, right? ABCD. Oh, everything that can appear in the heat map. ABCD, yeah. And it just basically says, if it's A, it's R1, B, it's R2, C, it's R3, D, it's 0. And you see there's a split personality there based on if it's a space or not. And then we do a search for this. This is additional null character sets that wouldn't normally appear during this process. And so this would be happening Yeah, each and every time. So this would happen each and every time. So if we went through all this, and then it still sees this, it's still going to ensure this gets taken care of, which is really good, because this is basically kind of just translate some information to let us know that we have this here. And there we go, okay, we're done. Whenever we get yo is greater than 0, and if cobalt is greater than or equal to the bond length. So we need both of those things to be true. You can't just have one of them be true. Because if yo is 0, then it won't work at all, because the very first process, yo is 0. And if cobalt is less than or equal to bond length, it won't handle the very last process, because it's in that values train. And instead of trying to create another number that just figures out the bond length plus 1 or something like that, fuck that. Just make sure it's also, because if we're not in the first process and this is true, then yo shouldn't be equal to 0 if we're not in the first process. So these are debuggings that I've done. I'll probably need to turn some of these back on to figure out what's going on. We can see we are actually removing some stuff. We see now we're dealing with airspace. We are now mixing air. This is for on-the-fly mixing of things right here at the end. So we are taking out these right here. Resetting gem and trackers. Huh. I don't think we've been getting that error anymore. Let's see. Orange, so we can delete orange, and if we take it and delete orange, yeah, see, it don't do that no more. So let me find the one what used to do that one. Alright, so that's O-R-A-N-G-E space I-S space A space C-O-L-O-R. So that is the error that we was trying to. I can't believe that's actually corrected that error. So this allows you to see what's actually there. This right here prevents that. Oh, look at that. Need a special worker. Can we do this? QOP, QOP. Is it already time for me to get my kid? Gosh, just about. I'm gonna have to stop here and redo this again. This wasn't enough time. Which is fine. So we can put. So here we have a spot where we can attempt to do some dynamic lattice measurements and stuff inside the mixture. This would allow us to have like some really fun stuff. That's not really needed, I don't think. Output. So this is the end. That's the end of that. So that's the end of the full house, right? Yeah. And then now here's the actual output after you're done. And it sets the input up for decoding. It sets the input up for encoding. Decoder below. So when I come back, we'll be just doing decoder, which is the part I know I'm having problems with. Okay. See you guys then.